Okay, so 12 o'clock, about time for us to get started. So first question, do people find these videos that I'm posting of the class useful? Anybody? So will I keep it up? Yes, okay. It's a little bit of a pain for me, but not too much, so if anybody finds it good, then I'm happy to keep doing it. Is the quality, like, okay? Solid okay? All right, I'm happy with okay. So then next thing is the test. It was on Friday. So I know what I thought of it. How about your feedback? Pretty good. How about time-wise? A little tight for time? For what it's worth, before I gave this test, I thought it was way too short. It was kind of considerably shorter than any test I've given in the past, and I was a little bit concerned that it was too short. So you might want to keep that in mind as we're rolling into the second test. Like, you might find that the next one is maybe even a little tighter for time, because we'll have maybe more topics to look at. I have not started marking them yet. I had 500 tests in Physics 1020, so I decided to get that out of the way over the weekend, so that was my weekend. I will start getting to your tests on the evenings now, so, you know, I'm going to shoot for the end of the week, but it might be into next week before they're done. I do have a TA helping me, but, you know, it just takes a little time. Okay, any questions before we get started for today? No, okay. So we did lots last day. We looked at conductors and insulators. We talked about what happens when you have a hole in a conductor, and we're going to go back to that idea today. So this is a super typical kind of problem. So what we have here is a point charge Q, that's this one, and it doesn't say anything about the sign of the charge, so I'm going to assume this is a positive point charge Q. It's in the cavity of an uncharged conducting shell. So if you're trying to imagine what this looks like, you have maybe like a bowling ball that has a thick wall and a marble smack in the middle of the bowling ball. So this is our conducting shell. It says that the conducting shell is uncharged. So the net charge on the conductor or on the shell is equal to 0. We can put that right there. And our first part of our question is, what are the induced charges on the inner and outer surfaces of the shell? So here's where we have to remember the behavior of what's happening in a conductor. This thing is a conductor. It means the charges are free to move around. This is a positive charge here, so negative charges are going to be attracted to those positives. So we're going to get some negative charges on the inner surface of that shell. That leaves the outer surface to be positive overall. Important to remember here, I've drawn these pluses and minuses. I didn't create any new charge. This is just the charges that were already in the shell moving around. Okay, so there's no total new charge. They've just moved around a bit. So the charge on the inner surface, I'm going to call that Qi. And the charge on the outer surface, I'll call that Qo. Together, they have to add up to give the net charge on that shell. And I know I could have just written 0 here, but I'd like to try just a slightly general approach for what if we didn't have an uncharged conducting shell. Okay, we all good so far? We'd like to find out what are those charges, so let's start going through the process. So I want to find the charge on the inner surface first. So I have to ask, what do I know about electric fields when I have a conductor? The thing that I know is that the electric field inside a conductor is 0. So there's my base bit of knowledge. To apply that knowledge, what I'd like to do is draw a Gaussian surface inside the conductor, so I can apply Gauss's law. Where I know what the electric field is, it's 0. Okay, so I want to use Gauss's law. To use it effectively, I need to use it at a place where I know the field, and I know the field inside is 0. So my next step is to draw a Gaussian surface inside the conductor. So my question is, what is Q inside? I'm going to draw Gaussian surface, I'm going shorthand here, GS for Gaussian surface, in the conductor, I'll capitalize and underline in, it's going inside the conductor, and the reason I've done that is because I know the electric field is 0. So I'll draw that Gaussian surface. I'll just draw an arrow so we know that's what we're talking about. Good here? That conceptual part is probably the hard part. Okay, so we've got our Gaussian surface. We're thinking about Gauss's law, so let's write down Gauss's law. The net electric flux through any closed surface is E dot A. It's equal to the net charge enclosed by that Gaussian surface divided by our constant epsilon naught. So we've already established that the electric field inside our conductor is 0. So this left-hand side, E dot A is equal to 0 because the electric field is 0. So what this tells us is that if we rearrange and solve for Q enclosed equals 0. And one more thing. So now, here's where things also tend to get a little bit tricky. You have to ask yourself, Q enclosed stands for the net charge inside the Gaussian surface. What's the net charge inside the Gaussian surface? So we have to look inside the Gaussian surface, so only inside the green dotted line, and we ask what things in there have charge. The two things that have charge are this inner surface and this point charge. So Q enclosed means whatever charges are inside that Gaussian surface. So Q enclosed equals 0, that's from Gauss's law, and Q enclosed equals Q on the inner surface plus the point charge Q. So those two things are both the same way to write down Q enclosed. So let's set those two to be equal. So 0 equals Q on the inner surface plus the point charge Q. Q on the inner surface is negative of the point charge. So there's that first result. This makes sense from a physical point of view. If I have a net positive charge here, the amount of charge is going to attract to that inner surface is going to be just enough to cancel it out. Okay, so two ways to think about it. Questions? Is that part okay? All right, next step is we also want to figure out what's the charge on the outer surface. So now we're coming back up here to this result that we wrote down as we were thinking about the problem. The net charge on this shell is 0 because it's uncharged, so we're given that. We know that the net charge on the shell is divided over the inner and outer surfaces. So Q inner plus Q outer is the net charge of the shell. So let's use this relationship to find the charge on the outer surface. Qi equals. So we know that Q of the shell equals 0 and Q of the shell equals Qi plus Qo. Put those two things together. Qi plus Qo equals 0. Qo equals minus Qi equals minus of minus Q equals plus Q. So to have a total charge of 0 on that entire shell, if there's minus Q on the inside, you've got to have plus Q on the outside. That's the only way we can get a sum of 0. Okay, questions? And like I said, this is a pretty standard problem. Not many ways we can shake it up here. I guess we could put in another shell, we can make this negative, we can make this have a charge, but there's not fundamentally much different you can do. Okay, next part of the problem, sketch the electric field. So now, in the back of our minds, we're going to remember that electric fields depend on the charges inside Gaussian surfaces. So inside the cavity means the electric field is only a result of that point charge. We know what the electric field looks like around a point charge. It's radially outwards. So inside the cavity is going to be pretty straightforward. Due to point charge. So I can draw that. So that's the first region. The next region to think about is inside the conductor. That one is super easy. The electric field is 0. There are no lines inside the conductor. And then our last bit is outside the conductor. Here we have to do a little bit of work to get to our answer because now we have a more complicated physical setup. We don't just have a point charge, we have a point charge and a spherical conductor. So to figure out the electric field, we're going to go through our process. So our process means we start with Gauss's law. The net electric flux is the integral of E dot A equals Q enclosed over epsilon naught. E dot A means the area of the Gaussian surface. Q enclosed means the charge inside the Gaussian surface. I keep saying Gaussian surface. I need to pick and draw a Gaussian surface. I have a spherical set of charges. My Gaussian surface is going to be a sphere. I'm going to give it radius r, and it's going to be outside everything because I'm trying to find the field outside. Okay, so once I've written down Gauss's law, I also have to show my Gaussian surface. So my Gaussian surface is a sphere, radius r, outside the shell. Okay, all good? So now, because I have spherical symmetry, I know that I have electric fields that point radially outwards. My area vector is also going to be radially outwards. So there's the normal vector, there's the area vector. So E and A are both radially outwards. Those two things are parallel because they're both radially out. So E dot A equals E times A times cosine of 0. 0 because they're parallel, the angle between parallel vectors is 0 degrees. Equals E times A. Because it's a sphere, the area is 4 pi r squared. Okay, so there's the E part, E dot A part. For my Q enclosed, I look at what's inside my Gaussian surface. I have two things inside my Gaussian surface that can have charge. I have the shell and I have the point charge. So my Q enclosed is my shell plus my point charge. So Q of the shell plus Q. Q of the shell, remember that was 0. 0 plus Q. So now I know what my Q enclosed is. So I have to put these things together. I don't think I can do it all on this page. So let's put the two sides of our Gauss's law together. E dot A is E times 4 pi times r squared. Q enclosed is plus Q. It's got to be divided by epsilon naught. So E is equal to Q over 4 pi epsilon naught times r squared, like a point charge. Remember, this goes back to what we did last day when we did the electric field outside a spherical conductor. We said once we're outside, it just looks like a point charge with whatever amount of charge that's on it. So once we're outside, all the spherical things look the same. What that means about our electric field lines is that they just keep going once we're outside. Something like that. Okay, any questions? So the next page in the notes, if you downloaded it, is basically just a plug and chug version of this problem. So you put some numbers in and do the same thing again. I'll get the solutions posted to that for you if you want to check it out. So that's a charge inside the cavity of an uncharged conductor. So your next question might be, well, what if the conductor did have charge? So what if it was a charge inside the cavity of a charged conductor? We're going to go through this one faster because it's basically the same thing. So let's see if we can just zip through this one a bit quicker. So in the cavity of a charged conductor, so this is telling us Q of the conductor is not 0. We've got a charge inside the cavity. I'll put in plus charge, but it still works if you put in a minus charge. We know that conductors have charges inside them. This one, let's say, has a net positive, so it might have a minus and 2 pluses and a minus and 2 pluses. Okay. So the charge might initially look like this. Then when we put the point charge inside, we still get the same sort of behavior. Negative charges get subtracted. Positive charges get repelled. And we end up with induced charges on the inner surface, Qi and Qo. So I'll write here, same behavior. And same treatment. So what I mean by same treatment is to find the net charge on the inner surface. We draw a Gaussian surface inside the conductor. We write down Gauss's law. We recognize that we know the E is 0, which is going to make Q enclosed 0, so we can find this inner charge. And we remember that the charge on the conductor is this charge plus this charge. Once we know this one, we should be able to find this one. So exactly all of the same behavior. The next slide in the notes is going to be a homework question, and I'm going to do one with like a spherical symmetry. I'm going to do one with sort of a weird symmetry. So here's our weird symmetry. We take a point charge minus 2Q, so we're trying to make this different as we go. So this one is a negative point charge, minus 2Q. It's placed within an irregularly shaped cavity. So this cavity just has this weird kind of blob shape that you're able to draw on Word. And the conductor holds excess charge of minus 3Q. So this is telling us the charge of the conductor. And this one is the charge that's in the middle of the cavity of the conductor. So this gray bit out here, this is the conductor. Q of the conductor equals minus 3Q. We get the same sort of behavior. Here we just have to be a little bit careful. I've got a negative point charge inside here. That means the positives are going to be attracted to the inner surface. And the negatives will be repelled to the outer surface. So same sort of behavior. So now Qi, we're anticipating that this is going to be a positive charge. Q on the outer surface, certainly it'll be more negative than whatever Q on the inner surface was. So this is kind of our physical setup. Are we good to here? So far we've thought about what's happening with a conductor. We're asked to find the net charge on the inner and outer surfaces. So let's go through the process. We'll write down Gauss's law. Net electric flux through any closed surface is the integral of E dot dA equals Q enclosed over epsilon net. Because we've written down Gauss's law, we need to pick a Gaussian surface. We want to pick one for convenience. I want to pick one where I know the electric field, so I'm going to put a Gaussian surface inside my conductor. So here's my Gaussian surface. And I put it inside the conductor because I know at this place E is equal to 0. Because it's in the conductor. So this whole term out here, this is going to be equal to 0. So this tells us that my Q enclosed must be equal to 0. And Q enclosed is also the sum of whatever charged objects I have inside my Gaussian surface. So the things I have charged are the Q on the inner surface and our point charge, which was minus 2Q. Okay, so my Q enclosed are whatever charges I have inside added up. Should be able to solve this for Qi. Qi equals plus 2Q. This matches the predicted behavior we had. We know that positive charge will be attracted. Enough positive charge will be attracted so that we cancel this guy out. And so this kind of matches an expectation that we might have had when we started the problem. Okay, next, what's the net charge on the outer surface? Here's where we remember that the charge on the conductor is minus 3Q. And we know that because that's a given quantity. That's in the setup of the problem. And the charge on the conductor, this goes back to property number 2, property 1, 3, I can't remember. All the charge on a conductor is on the surface or surfaces. Okay, so the charge on the conductor is whatever is on the inner surface plus whatever is on the outer surface. Put these together, we can find the charge on the outer surface. So minus 3Q is Qi plus Qo. Qo equals minus 3Q minus Q of the inner surface. Minus 3Q minus 2Q equals minus 5Q. Okay. All right. Excellent. So we've already gone through the first of our 4 properties of a conductor in electrostatic equilibrium. So the first property was that the electric field in the conductor was 0. The second property was that the charge has to be on the surface or surfaces. So now we've done lots of examples of what that means. Now we're coming to the third property, which says that the electric field just outside the conductor is perpendicular to the surface, so that gives us the direction, and it has a magnitude of sigma over epsilon naught. Here we're going to remember that sigma refers to the surface charge density. It's the charge divided by the area. So we're going to go through the process of seeing why that's true next. So I pose property number 3 as a question. What is the electric field outside the surface of a conductor? Here's our reminder of what charge density means. So sigma is charge density, charge divided by area. This is a 2-dimensional charge density. It has units of coulombs per meter squared. We've already seen this before, but here it is again.
Sorry, I'm actually still stuck on the previous example a little bit. It's just messing me up, like, how can the charge on the inside of the conductor be 0, but at the same time, like, it's also, at least in this example, like negative 3Q, like, how can there be 2 different charges? You know what I mean?
So it's just stuff moving around. At this moment, we have 40 people in the room. You're all sitting at your desks. Everybody could stand up here in front of the board. Still have 40 people in the room. They've just moved. Likewise here. The electrons on, you can think of the protons as moving around. So the charges are just moving around, but the total number of charges haven't gone anywhere. That's what this picture back here is. That's what this picture is, right? These purple ones are all the charges inside the conductor. We haven't made any new ones, we haven't gotten rid of any of them. But the negative ones have pulled to the inner surface, and the positive ones have pushed to the outer surface, but we still have the same number of charges.
So that's why we have QI and QL,
Yeah.
like together, like that's why the net charge is
Yeah,
in a
absolutely,
conductor.
yeah,
Okay.
okay. All right, any other questions about that? I know it's a little bit weird to think about, because we say charge is zero, and then it's all of a sudden it's not zero.
Yeah, if the last question, the cavity was irregular, if you had to draw the electric fields, would that be any different, or?
Oh, right, good question, I was wondering if anybody was gonna ask. So let's come to here. Why don't I throw this out there, can you draw those electric field lines? So we know point charges, so maybe you could do inside the cavity. We know lines of charge and we know planes of charge. Do we know weird little pointy bumpy things? No, this is hard, you can't draw this.
Oh.
Yeah. Maybe experts can, do a little bit of modeling. Yeah, but no, you can't draw this. Yeah, that's a good question. That's why this question didn't say draw the electric field lines. Maybe on the test it'll be, could you draw the electric field lines? Okay, so are we okay to leave that stuff behind? Okay, we'll come back to this one. So we're gonna try and find the electric field. So I've drawn a conductor here, I've got some charge on my conductor, and I wanna sort out what the electric field is. My charge density is two-dimensional, charge divided by area. We wanna find the electric field. I'm gonna deal with direction first. Okay. So I'm going to say that we're gonna go with the property, and we're going to outright state that the direction of the electric field relative to the surface is perpendicular. And if I had more room on my slide, I would probably write out of a positive and in towards a negative, because we know that electric fields go away from positive and in towards negatives. So why does it have to be perpendicular? So let's think about the fact that we're talking about conductors in static equilibrium. What does it mean that our conductor's in static equilibrium? It means the charges aren't moving, they're staying still. So if the charges are staying still, then the direction of the acceleration parallel to the surface, so that's our symbol for parallel. Our direction of acceleration, no wait, hang on. Our acceleration parallel to the surface is equal to 0 because it's in equilibrium. If the acceleration is equal to 0, then the component of force parallel to the surface is mass times the parallel acceleration is equal to 0. And our component of electric field parallel to the surface will be the force parallel divided by Q, also equals to 0. So since it's in static equilibrium, the acceleration is 0, which means the force is 0, which means the field is 0, all the parallel parts.
You mean the acceleration of the charges?
Acceleration of the charge, yeah, parallel to the surface. So these charges can't move left or right, because if they moved left or right, they'd be moving, but they're not moving, right? So A is 0, F is 0, and E is 0, all the parallel components. Which means that any electric field has to be perpendicular, because if it were parallel, those things would move around. So let's draw that electric field, perpendicular to the surface and out of our positive charges. So there's our electric field vector. So that deals with our electric field, so therefore E perpendicular is not 0. So our net electric field is perpendicular to the surface. So there's our direction. We also want our magnitude. To get to our magnitude, we have to go to Gauss's law. To use Gauss's law, we know we're going to need a Gaussian surface. I'm going to draw a Gaussian surface. That's a little cylinder. If you read an old text book, they'll call that a pillbox. I'll draw a little cylinder. My cylinder is going to be part inside the conductor and partly outside. There is a reason I'm picking part of it inside. You might know that already. If you don't, I will say it when we get there. So my Gaussian surface is a cylinder. Part inside, part outside. So now we'll think about Gauss's law. The net electric flux is equal to E dot A is equal to the net charge enclosed by the Gaussian surface divided by epsilon naught. For our net electric flux, it means the net electric flux through this entire cylinder, through the whole thing. So here when we think about the cylinder, my water bottle is the closest thing I have with me. It kind of has three parts, right? It has a top surface, electric field could get out through the top. It has a bottom surface, field could get out through the bottom. And it has a side surface, the field could get out through the side. If we want to find the total flux, we have to think about all three parts, okay? 3 parts to a cylinder, 3 parts to the flux. So, through my top face of my cylinder, we'll do that one next. So, through my top face of my cylinder, my flux is going to be E dot A. I'm talking about my top face right here. The normal unit vector points straight out, so the area vector points straight out. So the electric field and the area vector for the top face are both parallel. E times A times cosine 0 equals E times A. Okay, I can't take that a whole lot further, so I'm going to stop at E times A. Then I've got my electric field through the bottom face. This is why my cylinder is partly inside the conductor. My electric field in here is 0. So I kind of like this one. So that flux is 0. No electric field lines cut through that bottom face. And then for the tube or the wall of the cylinder, my E dot A equals E times A times cosine. The normal unit vector, and we did this when we introduced area as a vector, the normal sticks straight out of the side, so the area sticks straight out of the side. The electric field is perpendicular, the area is parallel, so those two things are perpendicular. Equals 0. So no electric field lines cut out through the side walls of that cylinder. Okay, so here are 3 parts to our flux. That means our total electric flux is E times A plus 0 equals E times A. So there's half of our equation. The other half of the equation is what is Q enclosed. So Q enclosed means how much charge is inside my Gaussian surface. The only thing with charge inside my Gaussian surface is that area on the surface of the conductor. We know how to find that charge. It's going to be the density times the area. So the net amount of charge is whatever charge is on that surface of the conductor that's inside that little cylinder I drew. Okay, now we put it all together. So we've got E times A equals sigma times A over epsilon naught. E equals sigma over epsilon naught, and it's perpendicular to surface. It's out of positive, and it's in toward negative. Okay, questions? So that was the 3rd property. The 4th property talks about this charge density. It kind of goes back to your question about drawing the electric field lines. The 4th property goes back to that charge density, and we're going to talk about electric potential energy and electric potential before we prove why that one is true. Okay, any questions? That takes us to the end of our chapter 22. We're going to start our chapter 23. I did write the assignment over the weekend, but I haven't had a chance to just proofread it yet, so I should get that open hopefully by the end of the day today, in case everybody's anxious to start the next assignment.
The assignment on the Q quiz, you mean, the one that's due on Wednesday?
So this will be a new assignment. I don't think it's open yet.
It's
No, I don't think so
But
yet.
there's one due on Wednesday, isn't it?
Yeah, that would be the chapter we just finished right now. Yeah. Usually those assignments are due a day or two after we finish the material. That's what I shoot for. Hopefully it keeps people working on them while we're doing it. Okay. Next, chapter 23. So for this chapter, I'm gonna assume that you all did work in energy in physics 1050 or 1020, and I'm gonna be drawing on a lot of those concepts from that course. So let's do a very quick recap of the things I think you know, or that you may wish to review. So first of all, kinetic energy of a system of particles. Remember that kinetic energy is a half mv squared. If you have a bunch of objects, you add up a half mv squared for all of them. So our net kinetic energy is the sum of all the individual kinetic energies. Okay, so that's kinetic energy. That's the energy of motion. Things have energy because they're moving. Potential energy of a system, use a symbol of U. That's an energy of interaction. And two examples you're probably familiar with would be gravitational potential energy. If we hold something up and I let it go, it's going to fall down. So it has the potential to move, it has potential energy. Probably also familiar with spring potential energy. If I put something on a spring and stretch it and let it go, it will start to move because it's stored energy in the spring. So that's an energy of interaction because we have an object kind of existing in the world. A change in potential energy, delta U, is equal to the negative of the work done. And we say that it's of the work done by the internal forces, so the forces in the system. So in the case of gravitational potential energy, delta U is the negative of the work done by the force due to gravity. Or delta U is negative of the force done by delta U is negative of the work done by the force of a spring on a system that has a mass on a spring. Okay, I think I finally got that out.
So, just to confirm, you mean the work that was done to move the system or to displace the system?
Yes, that would be moving an object, work done in motion. We're going to work on finding electric potential energy, so that's the first bit of this chapter. We know that if all the forces in a system, if they are conservative, and what we mean by a conservative force is basically not friction. Okay, so friction is a non-conservative force. There are some other ones, but friction is the one we think of the most. If we have a force that's conservative, we know two things. First of all, if the force is conservative, then it has a corresponding potential energy function. Gravity is a conservative force, so we have gravitational potential energy. Spring forces are conservative, we have spring potential energy. Electric force is conservative, we have electric potential energy. Okay, so that's the first thing. The relationship between the force and the potential is that the component of force is negative, the change in potential energy, the rate of change of that potential energy with that component of direction. So the x component of force would be minus du by dx, for example. So our force is the negative of the change in potential energy, and that's a relationship, comes from a relationship with work. Okay, the next thing we know is that our total mechanical energy is conserved. You've probably seen this written in a few different ways. So you might say E final equals E initial plus work done by non-conservative forces. So that might be a statement of conservation of mechanical energy you've seen. You might also see K final plus U final equals K initial plus U initial. So kinetic plus potential stays the same. Or you might see delta E equals delta K plus delta U equals 0. So any of those three expressions, you might run into any of those when you're in the help center. I tend to stick to the first one, so that first one is the line I'll start with in most problems, because I think that kind of is a big statement. Okay, last, work done by forces, and we're going to be talking a fair bit about the work done by the forces. Work done by a force is the integral of F over the displacement 0. So this is something I expect you've seen in Physics 1050. If you don't remember it, maybe 1050 was a while ago for you, you might want to go back and review through chapters 6 and 7. So that would be the integral of F times dr times cosine theta. If our forces are constant, and not all forces are, for example, a spring force is not constant, but if the force is constant, then our work done is F dot delta R equals F times delta R times cosine theta. That's the one you probably remember the best from Physics 1020 or 1050. So that one probably rings a bell. So we're going to be taking kind of all of these ideas and applying it to electric forces to develop electric potential energy, and from there we're going to talk about electric potential. Okay, are we still good? Okay. So when we developed the idea of electric field, we did it by comparison with a gravitational field. We're going to do the same thing here with electric potential energy. Your book has a slightly different flavor of this, so if you don't like the way I'm doing it, you might want to read your textbook and see if you like that way better. Over the years, I've tried to kind of smooth out the process. Maybe this year I'm happy, maybe not. They change it every year. So for gravitational potential energy, this will be a super fast recap. We know that any mass m is going to feel a force, a gravitational force, equal to its mass times g. That force is going to point towards the center of the Earth because the gravitational field g points towards the center of the Earth. So there's our weight, our Fg equals m times g. Notice here that Fg and g are in the same direction. And the reason that they're in the same direction is because mass is always positive. So right now it might set in the back of your heads like, well, wait a minute, charge doesn't always have to be positive. What's that going to mean about our electric stuff? So just kind of start wondering about that. So there's what we know about gravitational forces. So the force is m times g. We know that force. In Physics 1050 and 1020, we developed the idea of gravitational potential energy, which was m times g times y. We took the ground to be our reference level. So we say ground is equal to 0, and positive y points up. The work done by the force due to gravity is negative the change in potential energy, so it's minus m times g times delta y. That's how we would calculate the work done on an object by the force of gravity. And we know if the mass was going up, that work would be negative, so the force due to gravity would tend to slow it down as an object goes up. If the mass is going down, it's going to tend to speed up, and the work due to gravity is going to be positive. Okay, so we might be remembering here that work is also equal to delta K, so that might be coming back as well. And then the physical behavior that's kind of important for us to wrap our heads around is if we have an object and we release it from rest, it will always move to an area with lower potential energy. That's how the universe works. Things will move naturally towards areas with lower potential energy. So towards whatever ground is. This stuff okay? Yeah, so I think this is probably just a review for everybody. Now let's extend it to electric potential energy. So I've got the same kind of diagram. I've got an electric field that points down. I've got a charge Q in my electric field. To start with, I'm going to talk about a positive charge, what's happening. I know that my force is equal to Q times E. So if I have a positive charge right here, it's going to feel an electric force equal to Q times E that points down. Okay, so that's just from our definition of field and force. We know how those are related. So F equals Q times E is our electric force. I've been working on that one for a little while. U equals Q times E times S. So our gravitational potential energy, I don't know if I can get 2 slides up at once. Our gravitational potential energy was mg times y. our electric potential energy, we're not always gonna have things vertical, sometimes things might be horizontal, so instead of using y, I'm gonna introduce the variable s, but it's still the force times the distance. So this one is electric potential energy. We still need to define a ground and a coordinate system. With gravitational potential energy, we put the ground, y equals 0, on the ground, because that's very natural. With electric potential energy, it's a little bit less natural, but typically we choose ground, s equal to 0, at the negative plate. So the negative plate is our origin, and positive s goes up from there. So our distance s is measured relative to the negative plate. Our work done is still minus delta U, which is, oh my goodness, my delta went in the wrong spot. Minus Q times E times delta S. Okay, so same expression for work, negative of the change in potential energy. If we think about the motion, if our charge goes up or towards the positive plate, the force and the displacement are opposite directions. The work is negative and it's going to slow down. Charge goes up towards the positive plate, work is negative because force and delta R are opposite. That means it would slow down as it went towards the positive. That matches what we know about the behavior of charges. It's attracted to the negative, repelled by the positive, so it would slow down if we pushed it towards the positive. If the charge is left to go down or towards ground, the work is going to be positive because F and delta R are parallel, and it would speed up. So we get exactly the same behavior for our charge. If we release it from rest in an electric field, it will go towards lower potential energy or towards the ground. So at this plate, U is equal to Q times E times 0 equals 0. Up here, U equals Q times E times S is positive. So it will go from positive towards 0. So exactly the same behavior. All right, let's look at the negative charge. I think we're going to be able to get through it. Any questions about this before I move on to the negative?
Yeah, quick conceptual question there. So
Yeah.
for the positive charge, the work done upon it would be positive, and the net work would be negative?
So if this charge is moved towards the positive plate, the work done by the electric field would be negative. If it's moved towards the negative plate, the work done by the electric field would be positive. Yeah. And that, it kind of always comes from remembering work is F dot delta R. So if you know the directions of those things, you should be able to get the sign of the work. Okay, for our negative charge, so I've got my charge here, Q. This charge is negative. I'm still going to use the symbol Q, but Q is going to be like minus 100 coulombs, or it's an electron, or something like that. It's a negative charge. Here's where we're seeing the difference between gravitational stuff and electric field stuff. In gravity, masses are always positive, and electric stuff, charges can be positive or negative. This time my force is charge times electric field. That's going to point up, because my charge is negative, so the force is opposite the field. So same equation here. My electric potential energy is still Q times E times S. That's still the same. Still going to make my negative plate ground, so this is still S equals 0. If this is S equals 0, then down here U is equal to Q times E times 0 equals 0. Up here, U equals Q times E times S. This one's negative. Okay, because my charge is negative, that potential energy is negative. My work is minus delta U minus Q times E times delta S, same equation. This time, if the charge goes towards the positive plate, the work is going to be positive because F and delta R are the same direction. If the charge goes down, the work is going to be negative because the force is up and the displacement is down. If anybody printed off the notes, I made a couple typos there, so you might wanna make changes on your printouts. We still get the same behavior. If we release this charge from rest, it will move to a lower potential energy. If I let this negative charge go, it's going to move up here where my potential energy is negative and a bigger value than it is here, so it's still a lower potential energy. So that's maybe the big takeaway. If you let it go from rest, it will always go towards lower potential energy because that's what things do. Okay, we definitely don't have time for anything, so we'll quit there. Yeah, and then we're back Wednesday. Today is my day that I run to my next class, so I wouldn't have time for questions today.